We do a small reflection on a transformation that is affecting all of us. And there's going to be 3 axes to my attempt on this reflection. We're going to reflect on basically try to demystify a little bit what AI is, at least from the lens of MathWorks. And then what's happening right now? How is it affecting the engineering activities right now? And then speculate, imagine what it could be around the corner. So that's the basic 3 axes of this conversation. A little bit of maths. All modern artificial intelligence systems that you hear about, convolutional neural networks, even transformers, they're mostly matrix operations. Most of it, I would say over 90% of it, is really linear algebra. Not all of it, but most of it. The numerical computing is mostly linear algebra around 2 axes. One is training, the other one is inference. And that basically has been the case since early 90s to now. And so there's no wonder that there is some involvement with MATLAB. MATLAB itself, as an environment, has a long history with neural networks. Love affair started around 1992. I would say it's one of, if not the first commercial general purpose environment for training neural networks, investigating different types of neural networks, Whitroff and other folks who did that. And the neural network toolbox, I think, was 1992, June 1992, something like that. So it's a long history. Over 30 years it's been involved. And it's been used primarily initially for doing this research along both training and inference. Now, what's interesting is I'm in the model-based design part of it. I've got one leg in LTC, Language of Technical Computing, and one leg in a fancy integrator called Simulink. And so from Simulink perspective, it's a little bit different than MATLAB. MATLAB is involved both training, backpropagation algorithms, and inference, but Simulink is mostly on the inference side. And the reason for that is that to Simulink, edge AI is just like a block that you want to integrate in your system, test and verify, and maybe even get it to production code. So that's where it is. Now, I say Simulink sees edge AI as a fancy lookup table, and some colleagues think that I'm kind of trying to be humorous. It actually has a mathematical pedigree to it. Some of you may know there are 3 basic universal function approximators in mathematics. Okay? You have interpolating lookup tables. You have interpolating Gaussian kernels. And you have neural networks, convolutional neural networks. Lookup tables suffer from the curse of dimensionality. So they have a limit on scaling up on the inference side. Gaussian methods suffer from a curse of dataset size. So they suffer. They become very difficult to fit properly for large data sets. Neural networks don't have that problem. That's why they're succeeding. But there are universal approximation functions at high dimensions. They approximate intelligence. That's what we call artificial intelligence. Now, what's interesting is that these universal approximation functions, when you look at it at the level of that high dimensionality, they almost feel like you're dealing with real intelligence, which tells you something about it. These functions, the way these train, they only train for well-behaved functions. So let's be well-behaved, otherwise we're not intelligent. Anyways, so the relationship is not new to us, this area. There are 4 epochs from MathWorks perspective. One is the research era, around 1990s, when when much of the initial activity got a lot of folks excited in the research community. Then the breakthrough was a convergence of two things. One was the convolutional neural network training algorithms by pioneers like Jan LeCun and others, and coming together with availability of GPUs, starting with 2012 for general GPUs and all the way to specialized, optimized silicon for neural networks. So that's the deep learning plus GPU epoch, which basically took these pieces of mathematics, probabilistic mathematics, out of the research lab into real world. And that's the era of 2017 to pretty much now. And, well, of course, MathWorks, we responded into creating a whole bunch of applications for commercial production use. But now, we are on another epoch, which is the generative AI and now agentic AI tools. But it feels a little bit different. The pace of development, what's happening around us is breathtaking. So it's worth investigating into what it means to engineering. The key question in this context is, how is AI going to change engineering design? To get into that, I have a definition, which is not amazing. It should be iterative data-driven shaping of preferred solution within constraints. Decomposing that. Design is shaping of things into preferred forms. Anything. Ideas, molecules, anything. That's what design is. Engineering underlines the word constraints. There is some business aspect or pragmatic aspect to it. So that's what engineering design is. And the activity is iterative and data-driven. That has been the case. So none of this definition changes with AI. AI probably underlines two aspects of it. One is the data-driven part, emphasis on data-driven, and the agentic, this new thing that is only 10 months old. That underlines the iterative cycle, okay? So with that, probably the answer to the question is not changing the principles of engineering, but reimagining some of the design loops, some of the engineering loops. And that's how we look at it at MathWorks, okay? How we need to incrementally change the design loops that our tools are involved to be able to accelerate your pace of engineering and science. So the core purpose doesn't change, the principles of engineering doesn't change, but the design loops need to be reimagined. When you break this down into various thousands and hundreds of loops in engineering involved, loops within loops and all that stuff, it boils down to basically two basic patterns. In one, the human engineer is in the loop. And in this case, AI has been established, edge AI has been established as a component within a design. And it's increasingly so. And the reason it's changing, and that's important for us to discuss here, is that many of the new complex engineering systems, they're software defined. That is to say, the final design is not even done yet. So what you do, you have lots of actuators, lots of sensors, okay? And then eventually, if you haven't have application-specific sensor or aspects of the requirements requires that you need to have a new environment, you use AI to create a virtual sensor or have a reduced order modeling. So that is the phenomena within edge AI affecting many of the engineered systems. You see it in cars, but you see it in other places. The other one is agentic design loop, which I will dig into much further in this talk. And that one, the human is now out of the loop. The human has been replaced by avatar, by a digital so-called artificial intelligence. The human engineer now has to elevate higher value activities where you're really not designing the engineered systems, you're designing the design loop. You're monitoring it and you're constantly iterating on designing the design loop. It's almost like a design of experiment type of thing. So this part should be familiar to many of you. You basically take the AI as a component, inputs and outputs, and you try to apply it and target it to many systems, and we can do that. So I'm not going to get into too much into that. What's more interesting is generative AI at this point. And this slide is new. I had a version of this talk, when was it? About less than a year ago. And my emphasis wasn't so much on generative AI, but things have changed in only a few months. Here, you were talking about the classic generative AI. It seems to know about all the domains of engineering somehow. And you can also ask questions about pretty much every software tool that is more or less popular. And it seems to have very fast iteration, very fast way of creating ideas. So that's the agentic loop design. And so the speed of creation is no longer the bottleneck. Now, that poses problems. In the agentic coding loop, you have this basic notion that you want to get some goals and go through the iteration a few times, generate the code. You might want to make it more efficient by adding some skills. These are markdown files that you add in. And then you get an outcome. So that's the interaction of the aging coding loops that many of your organizations are looking at or you've already tried. We certainly are using it at MathWorks now. We've rolled it out to our engineering teams. And we're trying to figure out how to optimize the use of these and reduce the cost, because these tokens that are cost money, they cost energy. And so be able to control that, one way to deal with that is to add in skills. So it creates guardrails. Here's a key slide in this deck. If there was one slide I'd like you to think about, is the gap between what generative AI does and what engineering systems need or want or have to have. Engineering systems are celebrated by how deterministic they are. You know exactly what they're doing. You want to trust it. Generative AI, like a human being, is more or less a probabilistic system. You can control this thing called Boltzmann temperature in the transformer algorithm. And if you make the temperature too low, it hardly imagines anything. It's not so generative. So you want to have some non-zero temperature there. It's probabilistic. Where we think MathWorks will continue to operate is in that gap between probabilistic intelligence, biological or digital, doesn't matter, as always, and the engineered system. And that arbitrage is where I think is our core value purpose is. And now the question becomes, how does it specifically affect how model-based design should be used in future? And this is what we think about. Our current thoughts are as follows. If you look at model-based design, which is about systematic design, verification, and validation of ideas from initial concept to code, to production code. If you think about it that way, then, okay, how does it connect to generative AI? But generative AI is a probabilistic transformation into code right now. Those are the coding agents. So this arrow is probabilistic. This arrow from design to code in model-based design is not probabilistic, it's deterministic. So our idea is to move this arrow to here. That's our idea. Which basically means that instead of using these generative AIs to generate code, you have it assist your concept and your ideas, and you don't need to be probabilistic on the code generation side. That is already proven to be, there's a there's already a solution for it. You don't need to make it risky. So that's the basic concept here. And then when you get into that, let's just back up a little bit. 5 months ago, 8 months ago, if I was here, this would be the key slide. You have a co-pilot and you have an assistant chat with a AI, and then you in the loop, you get some ideas from the AI system, and then you act on it in model-based design. The agentic, where we are in the past few months, is to reverse the slope. So you're no longer in the loop. You're designing the loop. You're telling what you want, how you want it done, what are the guardrails, and you create that loop. You determine the goals. It goes and tries a few times. It fails quite a few times. Eventually, it comes up with some success and some outcome. So you're out of the loop, but you're in control of it. And the key thing is evaluations. The key thing is failing fast. The most important thing you can do with MathWorks tools is to fail fast. That's the best thing that we can do to provide you. We're not going to avoid your mistakes. We just want to make them cheaper. And that's essentially what the agentic loop is. And, well, if you think about that, we ourselves are trying to figure out what is the systematic use, how we systematically use that. Test-driven development seems to be the right way to go. And what is interesting is that the review process is less about now the design or the solution, more about whether the test criteria are correct. That's what we're finding within MathWorks, and I think that's what's going to happen in engineering design. Now, if we did that shift left, so instead of generating code, we use the agentic system to generate the ideas or the concepts at the level, at the domain-specific language, at its high level. We have the possibility to generate models from requirements, do high-level trade-off studies, do a whole bunch of things at the conceptual level, and leave the code to be deterministic, traceable, qualifiable as before. We don't need to replace that. We don't need a Swiss knife for code generation, in my opinion. Now, that's my opinion, and I think that's what we believe in. But this is expensive. You guys might be knowing. So how do we control that? And we talked about skills, which are basically, we need to introduce various type of information for the agentic system, friendly to the agentic system, so that they don't wear off too much and have too many loops around that design cycle. That would reduce the number of tokens. It would control the cost, we think. And this is much harder to do at the pure C or C++ code generation, because you're too far away from the engineering concepts by that time. It's much easier to do it at the high abstract level. This is our way to go. And then the trust comes from quality. And when you talk about quality, really is mathematical rigor. That's what it is. And that's also very difficult to do at the code level. You have to do it at a higher conceptual level. You need the fancy integrator called Simulink. All right? That's our opinion. And so the key concept here is to have autonomous failure loops in the agentic loop that occasionally succeeds and provides possible solutions that you finally have to sign off. And the trust comes from the rigorous, formal, or dynamic testing. And so the play button continues to be important. Now, where we are today, we have two ways that we're leveraging AI with model-based design. One is based on model context protocol server called MCP server. You must have heard of that. And that is basically a server that lives Central can cooperate with other MCP servers, and you can bring in third-party agentic environment that you might have or you might be thinking about, and we can introduce model-based design into that. All right? All your agents would know how to call our tools, how to call mathematics that is enshrined in our tools and take advantage. The other one is an in-editor experience where you have an MBD engineer sitting in Simulink environment and they want to do certain things. They want to have an assistant, they want to get insight. And so both tracks are valid, and depending on where you're sitting and what you're doing, you might want to do one. I would suggest you have to think about both. In summary, the love story continues. We love mathematics. You can do it now. And the timeless principles of engineering do not change, but you certainly should revisit some of the methods around your design loops. That's it.